So welcome. I want to talk a bit today about polars and what we've been building and what we've been building to build for scale. It's an important goal of polars nowadays. I'm going to talk a little bit about the history and about what we're aiming to do. I want to start a little bit. I did some small chit chat. Who here is Pandas users? Are Pandas users? Right. Polish users, yeah, and PySpark users. There's of course Databricks. Um, yeah, I'm gonna do a short intro. My name is Ritchie Vink. I'm the original author of Polars. I'm the CEO and co-founder of Polars, the company. I'm here with Giel. Giel and I started Polars. And originally I have a background in machine learning and software development. That's the relevant background, I would say. I want to talk a little bit about Polars and its goal when I started it. When I started it, I was bitten by pandas a lot, and I often had to work with PySpark in a corporate setting or in a professional setting. But it was always you were sort of obligated to use PySpark, but the data size didn't require that. And if the data size didn't require that, PySpark was sort of a pain to handle. And I wanted something easier. So the original design goals was the ease of pandas, though not the API. I didn't like the API. It was very hard for me to reason about what it was doing. And it was very procedural, which led to sort of unreadable code. You saw how it was doing something, but not what the intent was. And I wanted design for high performance. I was really enthusiastic about Rust, the language. I wanted multi-threaded. I wanted my laptop to be used with all cores. And Pandas never did it. You had a big journey. You saw one core chugging along and the other cores were doing nothing. They were just waiting. It was sort of very much an experience. And when I did research, I learned about what all the relational database systems were doing. And I was sort of flabbergasted that this was sort of ignored by pandas. No query optimization, no vectorization. So that's what I wanted in there. And I wanted Arrow native, so you can share data between processes. Arrow it's very popular. It's being used a lot. Back when I started, it was used in pandas. It had a lot of downloads, but it was not that known yet. It was sort of coming. I think Databricks also, or Spark also didn't have Arrow export yet. But it sort of was clear where it was going. And vertical integration was a goal. So that means that you also implement the IO readers. You do everything well, so you can control everything from start to finish. The goal originally was only in memory data processing. And yeah, that was the original goal. And that goal, Polars was very successful. The adoption is rapidly growing in all industries. And it reevaluated vertical scaling. That's because you can now have machines with a terabyte of RAM in AWS. So vertical scaling is much more interesting than it was 10 years ago, a decade ago. And you can scale out with a lot of cores. A decade ago, you had 2 cores on your laptop, and now you have 16 or 32. And in the cloud, you can get a box with 200 cores for $1. So currently we have 80 million downloads, and we're used at a lot of leading companies and used in many fields. But there were some problems because of the original design goals. We learned along the way, and we saw that we stagnated in getting really. We wanted more than this. We wanted to be faster and deal with more scale. Because single node processing can deal with more scale, but we're not hitting it. So that's when we decided to build a streaming engine. The streaming engine was the solution for this and is the solution for this, and really solved a lot of our problems. I'm not going to go through all of them, but I'm going to show a few of them and see what the problem was and how we solved it. So one problem we encountered was that the original engine was in memory only and did batch in memory. And that means that you have columnar data, you process data in a columnar fashion, but you do that on a full batch, so on the full column. That means you're not compute bound anymore, but memory bound. It starts your CPU is faster than your memory can fetch the data. So you're sort of waiting until for the prefetcher to load more memory, and that's sort of a waste. You have an idle CPU at one point. You're using all your cores, but your cores don't have to process to have to be used at full capacity. The solution here is morsel-driven parallelism. It's a very popular, popular vectorized query execution model. It's the state of the art in vectorized execution. It's sort of a technical term in relational databases. It's made popular by DocDB. It was not designed by DocDB, but they made it popular and showing that it's state of the art in performance. We also adopted that. And with that, you're sort of not memory bound anymore because you process your data in morsels. You do this parallel on every core, and your select operation followed by a filter will be processed by the same core. So you have multiple operations, and every operation works on the data that's still in cache on that core. So you will be a lot faster because you're not memory bound and will finally get CPU bound. It's sort of a very hand wavy because I'm not going to explain full morsel-driven parallelism here. But we implemented that with some adaptations. The adaptations I will get to a bit later. Another problem we had was materialization. If you think about pandas, everything is in memory. You do an operation, you get a full data frame. You do another operation, you get a full data frame. Polars didn't materialize everything. So if you write a Polars query, we scan, we select, we do some operations, but it always finished with a collect, and the collect is in memory, and then you write to disk or write to. This is sort of wasteful. If you have fully streaming operations, you don't have to first collect to memory. You can immediately sync them to a destination. It can be on disk, can be on S3, or can be a generator or whatever. So that's what we enabled with the streaming engine as well. You can now stream to a destination. And this allows you to process data sets that don't fit into RAM. As long as, if it's a fully streamable set of operations, you can process as much data as fits on your disk. So yeah, it's sort of a huge improvement there. And the other problem we encountered, it's not really a problem, but it's sort of a technical, interesting problem. We have a data frame data model. It's a relational data model. It is very relational, but it's not SQL. And it's not the same as SQL, and we decide ourselves what it does. And we want that because we want to meet the users at how they think about it and what we think PODAs should work at. But it's different. So order is defined. In SQL, order is not defined. A scope is allowed to access the full data frame in expressions. So an expression can be very powerful. It can actually do a join. It can do a filter. It can do a sort of that column. It can do getters. This is not possible in SQL without writing a common subtable. A common table expression. You always need to write a common table expression in SQL to be able to, if you want to access a sorted column or access an aggregated column, or getters don't exist. And in the literature is SQL. So if we want to do something like this, we have to invent it ourselves because it's our API and it's not something you can find in a paper. Of course, relational models you can find in a paper, but we're relational, but not completely the same. So here you have an example of how this Polars query, where in the select you can do something that looks quite arbitrary. You have a nested aggregation and a slice, but in SQL you have to write you have to write multiple CTEs, and you need to insert an order by to define the order because order is not defined. If you have a solution like Snowflake on pandas, then you have to insert indices. So they have to insert index columns and order by this index to make this order defined. And that means that they actually have to do a lot of sorts implicitly in the engine, which is fine. You will get the proper result, but it means that it will come at the cost of more compute if you want to do this data frame model in an engine that was not designed for this. So what we did is we solved this problem in our backend. We can now lower all the expressions to a streamable graph. This is the graph of the query you just saw. And we can now solve all our expressions in a streamable fashion. We can buffer, we can sort of we hide this complexity for the user, and we've been able to solve it internally. I'm really proud of this one because it was really hard to implement this, but sort of this allows us to take any Polars query and translate it into a streamable graph. And as a result, we did benchmarks on Polar streaming, and the performance is state of the art. So here you see PDSH, which is sort of, it's TPCH is very common database benchmark. This is scale factor 10, that's equivalent to 10 gigabytes of CSV data. I did scale factor 10 here so that we can still compare pandas, because that's sort of the main competitor here as well. But it's already 90 times slower here. Polar streaming is the fastest, then DuckDB, then Polars in memory. But we're on this dataset size, the streaming engine is 2.5 times faster than the in-memory engine. If we scale this up to scale factor 100, we see that DuckDB is the fastest scale factor 1, or a factor of 1, Polars 1.2, so it's the same order of magnitude. Polars in memory is 7-8 times slower, so the streaming engine can be 8 times faster than the Polars in memory engine. And Spark is 15 times slower, and Dask 30. We know why Polars just loses to DuckDB here, and that's because query 21, there's a range join we haven't implemented yet in a streaming manner. So that join will go into the in-memory engine, and then we're memory bound again. And you also see that the streaming engine is there 2 times slower than DuckDB because we're on the in-memory engine there. So this will get resolved. And that means so we're very proud that we're state-of-the-art performance now with Polars. So Polar streaming, it reduces your memory pressure a lot. It has state-of-the-art performance. We need out-of-core for pipeline blockers so that you can also process data sets so pipeline blocker, a sort, for instance, is pipeline blocker. You cannot do that in a streaming manner. You need all the data before you can sort. Then you want to spill to disk efficiently. We're also adding that's on our roadmap. It's designed around our Polars data frame model. This is very important because order in the data frame in our engine is cheap. It's designed in our engine. If you look at this image, and we have a serial source. A source generates morsels, chunks of data, but those morsels are ordered. They have an order ID, and they will get into a distributor that will do all kinds of parallelism, all works great. Once you need order, it goes back into a linearizer that does a little bit of buffering, very minor, and just checks the order IDs and gives them out in order. And this is very cheap, but very important. So we don't need any sorts to maintain order in Polars and still get morsel-driven parallelism. So that's Polar streaming. This will get you very far on a single node, and we're also want to go beyond that. And that's where we introduce Polus Cloud and Polus Distributed. Polus Distributed requires Polus Cloud because you're talking about managing multiple machines, sending your data there. The complexity gets a lot higher. So this is also a product which this is so Polus Streaming is open source. Polus Cloud will be a product. It will seamlessly move your data from your local development to a cloud execution. Think about it as remote execution. It's very common in SQL. You have a query somewhere and you execute that query, not in DuckDB you execute it on the same machine, but typically with SQL you run that SQL somewhere else. Your server is not your database server. So your compute server is somewhere else. And you can go for vertical scaling or horizontal scaling. We coin it somewhat diagonal scaling. We want to do both. Eventually we want to do the serverless, where we determine what kind of scaling is needed. Can it be done vertically or do we need to go horizontally? You pay only for the compute with a serverless experience. And we run in your own virtual private cloud. So this will look a bit like this. So you have your own environment. It can be your IDE, your Jupyter notebook, an Airflow orchestrator. There you have your Polus query. You send it to us, to our control plane, and you say, hey, I want this cluster with this amount of nodes. And we spin that up in your cloud. And then the query will be connected to your to the cluster we spin up for you. And in code, it would look like this. So let's say I have a query as a lazy frame. Lazy frame is the computation DAG of the query I want to execute. You can run that query locally, but let's say this query now takes a lot of data from S3, I cannot run that on my machine. Then I can say, for vertical scaling, give me a large box. Take this lazy frame, say remote, and execute it. This will run the query. On the main thread, you can continue your work. This will start an asynchronous query, and you can do your other work. And once you're done, you can await the result, or once you want it to be done. It's sort of similar to async await in that sense, but then you're not running on another thread or another task. The task is on another machine. And with horizontal scaling, it's sort of similar, but then you're not going into to a single node. You go to multiple nodes. Again, you say, give me a remote query, but then you say, I want this query to be executed in a distributed manner, and you execute that. You don't have to talk about partitioning or any of that. We will get the query plan. We will do the query planning, the partitioning, based on the operations you're running. Or you can do more. Think of lazy frames as task. You have a list of lazy frames, and you want to spawn many queries on a cluster and that's sort of where you yourself are more in control of what kind of task you spin. So that's what that would look like in code. We ran the benchmarks compared to PySpark Glue. And yeah, we're very happy with the results. Performance is great. We still see that streaming execution on a single node is more performant. That's because you have way less overhead, right? You don't need to shuffle data to other machines, and shuffle overhead is big. But once you go beyond the scope of vertical scaling, then distributed can be much more interesting. Or when you go into more embarrassingly parallel queries, then distributed as well can get way more I/O loading from S3. So yeah, we saw that distributed is about 16 times faster. Streaming 16 times faster and distributed 8 times faster than PySpark Glue. So you talk about going from query that takes an hour to 2 minutes. And other things that we're building is on our immediate roadmap, we're building extension types. We really want to have that because it will open up different domains. We don't support directly into polars. So those domains, geo, AI, multimodal data, we can then support with extension types. We will also stabilize IO plugins. We would need to redesign them a little bit, but that's also on our roadmap. Take these three. If you have extension types, plugins, and IO plugins, you can take polars and build your own domain, be it geo. If you have a geo paquet file with the stable IO plugins, you can say this is this is what I need to read, or I have this very strange proprietary data file. I want to read it as this data frame. You can do that with IO plugins, and then you have maximum performance. It will hook into our engines. Combine it with plugins, you can do your own domain logic. And with extension types, you can make sure that if you have an image data type or whatever custom data type, it will remain the data type. And we will be a superset of PyArrow types. That means that everything that exists in PyArrow data types, extension types, we will support, but we will also support function pointers. So you can say, hey, this is hashable, and this supports hash and equality, and therefore we can use it in a hash join, for instance, and therefore you could get a join. It can be used as a join operator or a join key, that kind of stuff. We will support generators, so the streaming API can be synced into generators, into Python generators. We will default to streaming in our lazy API. That's very soon. We're working really hard on a lot of native Iceberg support. Iceberg is a lot more complicated than we initially thought, but we're very far now, and it will also have full distributed support there. And we're working hard on extending Polars Cloud also to on-premise and Azure and GCP. Initially, it's AWS only. Yeah, and our launch is very soon, so that's in September 2025. So give it a shot in a few months. And that's it for scaling on Polars. If you have any questions, please. Thanks.
It sounds like Polars Cloud is choosing the compute for you, right? To optimize a certain query you have. How often are you scaling horizontally instead of vertically? It seems like you would always max out vertically and then go horizontal. Does that sound about right?
If we decide what kind of scaling we do, is that sort
It
of
seems
question?
like that's what Polars Cloud is doing, is deciding the compute to optimize a query, if I'm understanding correctly.
Yeah, but currently it's still up. You choose what kind of scaling you do. Eventually, we want to do it for you. If we do the serverless part, we decide if it will be horizontal or vertical. How could we do that? We can, on a query, you can see some things are embarrassingly parallel. So if you have a query where you only select columns and do filters and streamable operations, it's completely horizontally scalable. There's no synchronization whatsoever, so it will always be faster to do that horizontally. If you have a lot of joins, it depends. If you have some operations require order, and there it's probably always, if your data fits on a vertical box, it will be cheaper. Yeah. So we can inspect the query and make decisions based on that.
Thanks.
Can you scroll back to the slide where you showed the results for TPCH distributed? Yeah, maybe I'll have some questions later. I'm just gonna look.
Okay. So he'll take a look and think of some questions.
Yeah, that's right.
Any other question?
So based on this graph, it looks like the performance of Polars versus, the other libraries, you can't even compare. It's so much better. So, like for an existing team that may have, expertise and code in one of the existing frameworks, what do you consider as like the barrier of entry or friction from going from that stuff to Polars?
Depends on the framework, probably. So pandas, I would say it's just move. It will. I mean, if you're an engineer, you have a lot of experience in pandas. This will, it's you have to you need to learn a new API, and that's sort of painful. But still, a lot of people do it, and it's worthwhile because we will give you a lot less bugs. It sounds very strange, but we're strict, and strictness upfront saves you a lot of time. Strictness means, hey, we give you an error, this data type doesn't match. We do that before we run the query. In Pandas just executes every operation. It doesn't know what it will execute 20 minutes or 2 hours into the query. So if you made a mistake, depending on data types, for instance, if you made a data type mistake that became clear 2 hours in the query, then it will fail at 2 hours in the query. It will cost you a lot of iteration time, a lot of wasted compute. We will give you that error, that bug you made. We will give you that upfront, so that will save you a lot of time. In Polars, you can scale out. If you're on PySpark, there are still distributed cases where PySpark would still be a better choice, but there are a lot of cases where Polars is way faster, is way cheaper. Yeah, and I think that's actually on 80-90% on the queries, especially with vertical scaling nowadays.
Yeah, because just if I was to show this graph to like a manager or decision maker and say, this is the performance, these are the, we're efficiently using CPU, GPU, reducing cloud costs. It's like a no-brainer.
The numbers are real. Yeah.
So, I mean, if the only barrier is now you need to worry about types, then it's like learn types.
Yeah. So I agree with your conclusion.
Thank you.
This is a Parquet file you start, the iceberg.
No, this is not iceberg. This is TPCH with Parquet files, indeed. So as local. No, Polars Cloud. This is S3. Yes. Yeah. So there are 700 megabytes per file, something like that. So you have multiple files. The metadata is in every file. The data is on S3. Yes. Yeah.
Does Polar support SQL API?
Yes-ish. We're very good at data frames. That's where our niche is, where we're very good at. That's where we focus most of our time on. We do support SQL, but it hasn't been a focus yet. I think in 1.5 years, we will probably make that more complete and say, okay, we're going to take that very serious as well. But that's not our main goal yet.
Is there like a BYOC offering for the cloud, or is it just?
Yes, bring your own cloud. Yeah.
I see.
Yeah.
What about self-hosted?
We're not self-hosted. It's self-hosted as in on-premise, or yeah, we're building that. Timeline, Giel?
A little bit later, towards the end of this year, probably.
Yeah, but it's so to give you a little bit insight there, Polars Cloud, we have a control plane that spins up the hardware and spins up the cluster, and on the cluster we will set up the executor and workers. But that we call that the compute plane. That compute plane can also run on premise. So for us to be able to work on premise, the engineering cost is not too high. You will get the same the same software, But of course, we need to make some adaptations. Especially the more complicated part is everybody's local on-premise situation is a bit different. All right.